Arden Labs, specializing in high-performance software consulting, training, staffing, and development. Module 8, Go Routines. You are now watching Lesson 8.2, Go Scheduler Mechanics.
With the operating system mechanics in place, with understanding concurrency and workloads, now it's time to learn about how the Go scheduler semantics work and how it sits on top of the operating system. So when your Go program starts up, what the runtime is going to do is try to identify how many hardware threads you have on that host machine. I've got 8 hardware threads on my machine. So that means that when any program starts up on my laptop here, I'm going to be getting 8 of these logical processors, 1 per hardware thread on that machine. And every logical processor is given a real live operating system thread, exactly what we had talked about, and that operating system thread will execute on the hardware. And remember, the operating system is still responsible for making sure that those operating system threads get on the hardware. And then we have one more thing, which is the Go routine. Now, the Go routine is an application level thread. So remember what we have here. We have our app layer thread, we have our operating system level thread, and then we've got our hardware level thread. We've got these 3 layers that are all working together, okay? And we're really a layer of indirection away from the hardware. We talked about how those operating system threads work, right? We talked earlier about how they have stacks. Go routines have stacks. Operating system threads can operate in one of 3 states. They can be waiting, running, or runnable. Guess what? Go routines can be waiting, running, or runnable. From my perspective, that Go routine or application level thread is almost identical to those behaviors that the operating system threads have. The only difference, the only difference is that that Go routine doesn't have priorities. And one of the reasons Go routines don't have priorities is because we're not dealing with events up in our application space. The operating system has to deal with events, we don't. So everything we've talked about applies at the Go scheduler level, even though we're a layer above the operating system, except for those priorities, which is great because, again, they're not really going to make us necessarily a better Go developer. Okay, so here we are. This is our model, the P, the M, the G, with an M for every hardware thread. Now, what I'm doing is I'm showing you a single-threaded Go program now, right? Like the Go playground. Now, another thing about this scheduler is that we consider it to be a cooperating scheduler, which means that we need events that are occurring at the application level to perform scheduling. But these aren't like hardware threads, or sorry, hardware events that are happening in this like preemptive mode where we're not really sure, right? Because this is a cooperating scheduler, what this means is that we've got to find safe points in the code that we can yield these Go routines on and off that M. That's what we're looking for. So the job of the scheduler is to behave like the operating system scheduler in that there are time slices and that there are events, but our events have to occur at safe points. And right now today with Go, and we're at least in 1.11, that these safe points happen during function call transitions. So we're waiting for these function call transitions to occur in Go. Now, they're looking at in 1.12 and maybe 1.13, but at least they're looking at 1.12 to add some preemptive techniques to the scheduler to make it a little bit more random, similar to the way the OS works. But for now, today, as we're talking, the Go scheduler is a cooperative scheduler. That means Go routines have to yield their time. And instead of asking developers to call yield, the Go scheduler is the one that's calling yield on behalf of those Go routines. Again, under the idea that there's a minimal time slice and all that good stuff. So let's take a look at that here. Now, there are really 4 classes of events that can occur with function call transitions that give the scheduler an opportunity to make a context switch. All right? We've got the keyword Go. Anytime we've got a Go routine that we're going to be creating, there it is. And in fact, when we create Go routines, there's actually 2 more data structures here. Every P has a local run queue. And that's going to be for Go routines in that runnable state. So if we use the keyword Go in front of a function call, we're going to end up with more Go routines. Go routines in a runnable state will end up in some local run queue. Go routines that are executing right there on the M. And there's actually another data structure called the global run queue, which is another queue of Go routines that are in a runnable state but haven't been assigned to a P yet. Okay, so there's Go. Garbage collection. Anytime the garbage collector runs, there's going to be a lot of chaos here, and you're going to see a lot of scheduling happening. We're going to see that when we get into some tracing later on. System calls. Anytime there's a system call that occurs, we're going to be making system calls quite a bit. There's lots of system calls that are going to happen. You're logging, you're producing output, you're hitting the network. Almost anything you do outside of your app is going to be a system call in Go. And that's going to give the scheduler an opportunity to make a scheduling decision. Remember, these are opportunities. It doesn't have to happen. There's still minimal time slices. There's still moments where we've got to get into these safe points. But there are opportunities for the scheduler to yield Go routines on and off that M. And by the way, taking a Go routine on and off the M is what we call a context switch in Go. Remember, the context switch at the operating system was 1 to 2 microseconds, 1,000 to 2,000 nanoseconds. Here in Go, that same context switch, that's going to be roughly 200 nanoseconds, about 200. So a significant difference in the context switch. That's going to help us too at the Go level. So we're going to go from like 2,000 to 200, right? Really great. Okay, system calls. And there's two types of system calls. There are asynchronous and synchronous system calls. We're going to have to learn how to do with that. Now, the last one, we got the use of the Go, we got garbage collection, we got system calls. And there are other types of blocking calls that are going to happen in your software. In multi-threaded software, these blocking calls could be synchronization and orchestration, mutexes, atomic instructions. You also have potentially CGO issues. CGO is the C compiler for Go, so you can call into C libraries. And in cases where we've got C functions that could be blocking that M, we've got to be able to detect that. So we'll talk about that as well. All right, so we've got our 4 classes of events that are occurring at the scheduler that give the scheduler an opportunity. The 2 interesting ones really are the system calls and those blocking calls. So let's go a little deeper into how those work. So Go has something that's called the network poller. And the network poller starts out with a single thread. And ePoll or K-Event on the Mac and IOCP on the Windows, those kind of thread pooling technologies, that's what's being used here with the network poller. And the network poller's job is to handle asynchronous system calls. Asynchronous system calls. And we call it the network poller really because the only asynchronous system call we really work with today are the networking calls. All 3 operating systems have excellent support for that asynchronous networking. Excellent support. Unfortunately, the operating systems, except for Windows, doesn't have strong support for file I/O in an asynchronous way. So anytime we're doing file I/O, we're going to be using those synchronous system calls. When we're doing networking, luckily, because the real bulk of the work we do is over the network, we're going to be leveraging asynchronous system calls and the network poller. So let's run a quick scenario here with the network poller and our asynchronous system calls. Let's say right now, this Go routine, what it's doing is it's going to be wanting to perform a read operation. There it is. It's going to perform a read on the network. So as soon as that happens, what the scheduler is going to do is going to say, no problem. Since you're about to perform a read, we're going to take you off this M, and we're going to put you right here on the network poller. We're going to issue that asynchronous system call, and you're going to wait here until the operating system can complete that read operation. Now, what's brilliant about that is we've taken the G off of this M, we've moved it onto essentially another M or a pool of M's over here, which frees up the M to do more work. So now the scheduler can come in, choose another Go routine from the local run queue for that P, and we can start getting some more work done. Remember, that's that 200 nanosecond context switch, but it's helping us here because that M gets to stay busy doing more work. Now, once that system call is complete, we'll take that Go routine off the network poller, we'll bring it back into the local run queue, and we can start all of that again. Really great workflow here because we're efficiently using the threads that we have. But what if this read call wasn't a network call, it was file I/O? Now we got a little bit more complication. We can't use the network poller anymore. Might as well not even be there. So what are we going to do? Because the last thing we want is this Go routine to block this M. If this Go routine makes a read call to open up a file, which is going to take a minimum of a few microseconds of time, well, we're not getting any work done during that blocking. We don't want that. So what the scheduler is going to do is, identify that this Go routine is about to do some file I/O read, and it will take this M, and it will take this G, and it will detach it off that P. And there it is, right there. That Go routine now blocks that original M right over here on the side. We move it off. But now we're still not getting any extra work done. So what's going to happen? Well, we're going to bring in a brand new M. Now, if we've already have an M that's parked, brilliant. But if we, we'll just bring it in and we'll get it going. But if we don't, we'll have to create one. And now what we can do is take another G off the queue and get it running. So we're still able to get a lot of work done here. It's just that we have to create a new thread in this case to make that happen. What happens once that Go routine system call is complete? Well, once that's complete, we're going to take this G off that M, we're going to put it back into the local run queue, and now what we're going to do is park this M over on the side when we have to do it again. The chance that this Go routine is doing the same sort of read work is pretty good, so we'll see that whole transition happen again. Now, what if this Go routine is doing some other sort of blocking work? What if, like with the C library? Remember something about Go. When Go first got released about 8 years ago, we had a great standard library, but a bulk of the third-party libraries that are out today, like Kafka, for example, wasn't there. We needed to rely on a lot of the C library support early on in Go to be able to write programs. And since Go manages memory in its runtime, C isn't part of the runtime. These are also decisions that had to be made on an engineering side. So the problem is that as soon as we call into a C function, we're kind of out of our managed state. So how does the Go scheduler know that a Go routine making a C function call isn't now going to be blocked for a long period of time? Well, there's another thing that's part of the scheduler. It's called the system monitor. And the system monitor is monitoring these Go routines and the work that they're doing. So let's say what's happening is this Go routine is making a read call, but it's from some sort of C library. What the system monitor is going to be able to do is look to see how long it's been since that Go routine is executed an instruction. And it's a little bit of an interesting algorithm, but for our purposes right now, 20 nanoseconds is that base time period of inactivity. So essentially, if the system monitor notices that this Go routine has been inactive for 20 nanoseconds, it's going to assume that it's blocked. And then we're going to go through the same exact cycle that you saw before. We're going to move that M2 off with the Go routine that's making the C call that's blocked. We're going to bring another M in, and then we're going to be able to pull another Go routine from that local run queue and keep things going. So when the system monitor identifies that something is stalled for about 20 nanoseconds, it's the same kind of activity that we saw with synchronous system calls. The goal is to keep those Go routines running that are in a runnable state. And ideally, the asynchronous system calls give us the most efficiency because we're not creating and parking new threads. We're leveraging the operating system threads that are there. It's one of the reasons that Go is so fast with its networking. because we're leveraging those asynchronous system calls really effectively. Okay, let's kind of take a look at everything that we've now done and sum up some of the efficiencies that we're going to get from this programming model. And another really cool efficiency, actually, when we think about it, is when we start dealing with running Go routines in parallel. So we've been demonstrating a single-threaded Go program. Look at what I have now. Now I've got a multi-threaded Go program. There it is. I've got 2 Ps, 2 threads, each thread on its own hardware thread. Now these Go routines, right, this one and this one, can run in parallel. I now have 2 Go routines executing instructions on 2 operating system threads with 2 operating system threads running on 2 hardware threads. Now we're able to run Go routines in parallel. Again, we have to think about our workloads, IO bound and CPU are blocking, right? IO bound and CPU bound, but this is what we're going to have. Now, another interesting thing here when we've got these Ps is that the Go scheduler is also a work stealing scheduler. Think about this right now. I've got 2 Go routines running in parallel. I've got 3 Go routines in queue here. I've got 1 Go routine in here. And let's even imagine that I've got 2 Go routines in the global run queue. They haven't been assigned to a P yet. So imagine this scenario. Suddenly the P over here on the right, this P finishes all of its work. There is no more work for this P to do. What's going to happen? Well, Go is a work stealing scheduler as well. We have this, right, CPU capacity here, but it's not being leveraged and we want to use it. So there's a little algorithm around work stealing. And part of the algorithm says, go see if there's another P with a lot of work in it. And if there is, steal half the work that it has. In this case, this is a P that has 4 Go routines. So quite possibly, what that P might do is steal half of the Go routines here, put 1 in queue, and start executing the other one. Work stealing. We'll definitely do some of that. And when that's happening, when the work stealing is happening, what we say is that M is now spinning. Remember, the last thing we want is this M to fall into a waiting state, because then it will be pulled off that hardware, and we're not going to be able to execute Go routines as quickly as we otherwise could. Now, imagine if this P suddenly finishes its work. Now, it's got no work to do. Maybe it wants to steal some work out of this P, but there really isn't a lot. Another part of the algorithm says, you know what, another place you can look is the global run queue. In this case, there are 2 Go routines in the global run queue. Most likely, this P is going to come in, steal work from the global run queue now, and we'll get that work going as well. So work stealing is a big part of the scheduler, especially as we start to have the ability to run Go routines in parallel. All right, with that in place, let's do a small little exercise to kind of see the real sympathies here that we're getting from the Go scheduler sitting on top of the operating system scheduler, sitting on top of hardware threads. All right, now let's start with a multi-threaded program at the operating system level. And what we're going to do is create 2 operating system threads. Here's thread 1 and thread 2. All right, 2 operating system threads. Maybe this is a program written in C. And what these threads are going to be doing is passing messages back and forth. It's not important how they're doing it. What's important is that this is IO-bound work. So we're waiting for some sort of context switch to get into that executing or running state. And then we're going to do a little bit of work, and then we're going to send that message across to the other thread. Now, when we send the message across to the other thread, we're going to context switch off because we're no longer going to be running. We're now going to move into that waiting state. We move into a waiting state, we come off the core. Let's say that we're on core 1. Okay. Now, when that message shows up on the other end, there'll be an event to let that know. Then we're going to have a context switch, right? We're going to move from that waiting state to a running state. Then we're going to need that context switch to move into an executing state. We're going to pick the message up. We're going to do some work. We're going to send that message back. We're going to move into that waiting state again. Now we're going to get an event on this side. We're going to go from that waiting to running. Then we're going to go into that executing state. And we're going to do this, and we're going to do it again. Every time this thread passes a message back and forth, we're going to have context switches. Maybe this was also on core 2, right? Maybe this ends up being on core 3. We're also going to be bouncing cores because we don't really know which core is idle at any given time. So you can see that with this IO-bound workload, we've got context switches going from waiting to running to executing. We're doing a little bit of work. We're passing messages. We're moving around. We're bouncing around cores. Okay, good. Let's switch over now to the Go scheduler. When we use the Go scheduler, this diagram actually is going to stay the same, but I'm going to add just a couple of little changes to it. Let's change these from T's now to G's to represent that Go routine. Okay, Go routine 1 and Go routine 2. And let's also do something interesting here. Let's set up just a single P with a single M running on a single hardware thread. Let's just say that's running on core 1. Now, if I do all of that, the only thing that changes is what core we're running on, because we know that we're only going to be running on core 1. But what's interesting is that this is IO-bound work. So the rest of the diagram stays the same because the Go routines have to transition in the same states as those operating system threads did, right? The only real difference here is that instead of these context switches taking 1 to 2 microseconds, they're now only taking roughly the 200 nanoseconds, right? We just went from 1,000 to 2,000 nanoseconds down to about 200 because the context switches are happening here on the thread. They're not happening on the hardware. If you step back and look at this a little bit more, what you're going to see is really where the magic is. Because what Go has really done is that it's turned IO-bound work into CPU-bound work at the operating system level. Take a look at this again. The context switches are absolutely happening, but they're happening at our application level on the thread. From the operating system's point of view, this M is always running, always in an executing or running state. Always, always. From an operating system's point of view, we are doing CPU-bound work, even though it's really IO-bound. And this is one of the reasons why we don't need more threads in our Go programs than we have hardware threads, because the scheduler is converting all of the work that we do, CPU and IO-bound work, always into CPU-bound work at the operating system level. And I told you in the operating system mechanics, the most efficient work that you can do is CPU-bound. It's also the simplest because we know that we only need 1 thread per hardware. And if we're doing concurrent work, then we know how to maximize our efficiency, right? More threads than you have cores never is going to give you better throughput. That CPU-bound workloads are beautiful. And what Go has just done is it's reduced a huge amount of load off the operating system because the operating system basically just maintains a level of CPU-bound workloads. We could use a lot less threads, which cost us more, right? And since we're using less, that cost is less. And since the context switches cost a lot less, right? We're going again from that 1 to 2,000 microseconds of context switch nanoseconds to 200 nanoseconds, then even these transitions between states are happening a lot faster. This is the real beauty. This is the real synergy of what's happening here and the mechanical sympathies between the two schedulers. But I want to stress something very, very clearly. Even though we've got this scheduler that's doing all this wonderful stuff, you still have to be sympathetic with the scheduler. In other words, we still have to know what our workloads is, okay? More Go routines than you have M's for CPU-bound workloads are not going to make you get your work done faster because you still have 200 nanoseconds, right? That's like 2,400 instruction losses that you're gaining or you're hitting when you have a context switch. And if it's CPU-bound workloads like adding numbers, that's still 2,400 instructions or 2,400 numbers you could have added that you're otherwise not adding because of the context switch. When it comes to IO-bound workloads, we're going to gain real efficiencies here because that context switch is less. And again, now we can have more Go routines than we have, let's say, M's. And what's really brilliant is that that application thread, that Go routine, is so lightweight that for the first time in our programming models, we could build a web service that could throw a Go routine at every request. In other words, we could have 50,000 Go routines in flight. Right? It would be reasonable and practical to do that. And those types of programming patterns are a lot simpler than trying to figure out what is the magic number of Go routines we need to create for some sort of thread pool here. This is some of that cognitive load that Go is taking off our backs. Instead of just saying, let's find some magic number, let's just throw a Go routine at every problem that comes into the server, every request, every task, and let the scheduler handle it. And it may not be the fastest way to solve the problem, but guess what? It tends to be fast enough. And remember what we're always going to be talking about. We need to balance the performance with the complexity. If it's fast enough, and you've reduced a huge amount of complexity, that's a big, big, big win. If you're looking for pure performance, really, Go is not your answer. You've got to start looking at C again and assembly, maybe even Rust. Rust looks like a really interesting language to me. But if you're going to have the mindset that it's fast enough, now this programming model, this multi-threaded programming model that Go's given us, is really reducing load, cognitive load on us. We still got to know what our workload is, right? Got to know when we can leverage and not have to leverage parallelism. We still have to know these Go routine states. Less is still more. Complexity needs to be less. This stuff is complex. But we have these opportunities now thanks to Go. So moving forward, we're going to take these mental models that we now have of the operating system scheduler and the Go scheduler. We're going to start looking at code. We're going to start understanding what it means around synchronization and orchestration, because that's on you. We'll talk about that stuff. We'll start looking at code. We'll start looking at patterns. And I'm going to do my best to try to at least give you the knowledge and the tooling so you can make some better engineering decisions as you start to write multi-threaded software in Go.